So I think other participants will come soon. So now we will start our last day session. So this is our 11th session, and from 11 to 12 we are a little bit late, and then after 12 to 1 my session will be there. So today complete session will be covered by till 1 p.m. Then after 1 to 3 you can enjoy your lunch, and also if you want you can go to our conference venue. Okay, then after we can go for you can say 3:15 one exam would be conducted, and 3:15 to 4 o'clock, and then after we will go for we can say the valedictory session where the certificate distribution and other things will be happen. So thank you for this one, and now I would like to invite Professor Müller sir for today's session.
Hope it doesn't make noise. Okay, okay, is it on? On? Now it should be on. Okay, then let's resume where we left off yesterday. I would like to finish this topic from yesterday, and this was about the what you call the inverse kinematics of an open kinematic chain, like a robotic arm, right? And this is what we discussed, so this is not unique. And we have to distinguish between the geometric inverse kinematic problem and the velocity inverse kinematic problem. The velocity inverse kinematic problem is relatively simple because it's just it boils down to somehow invert or pseudo-inverse the Jacobian, whereas the geometric inverse kinematic problem boils down to actually invert this mapping. So essentially, it's saying we have this product of exponential, and this is a function of q. It takes the joint coordinates and it gives you the end effector pose. And now you're asking, okay, what are the joint coordinates? It would give you the end effector pose that you're aiming at. And this, as you see it here for an example, for a 6-degree freedom robot is not unique, and this is giving you certainly a bit of headache. And the question is how to do it. And this non-uniqueness problem remains for whatever we do. But the basic idea is to solve this numerically, right? And what we said is that we discussed. That's what we left yesterday. This is where we finished. The whiteboard is gone anyway. This is where we finished yesterday by saying how do we compute an error? That means a distance, in quote unquote, and that is of course by the inverse of the current one times the desired one. You can do the opposite, and anyway, it gives you some sort of distance measure, so to say, or difference, if you want to say, or you can call it error measure. And now this is where we stopped yesterday, and now I need a whiteboard. Now let me just do it. Somehow. Oh, that one. Mm-hmm. There we go. There's something new on it. PPR. Yeah, we should maybe have a wipe if you find one. Yeah, there too. Yeah, thank you very much. Thank you. Okay. How did we define? So how did we define the body fixed twist remember we had the body fixed twist defined as like something like there's this omega vector, and then we have the little v, the linear velocity, and this gives you the what you call a twist, right? And we had the b on top or something just to say this is in body fixed coordinates. And how did we define it? We defined it actually by taking the inverse of our H matrix times H dot. Okay, and then what it gives you is this matrix omega tilde little v 0, 0. And then we said, okay, we can actually uniquely identify the 6 vector out of this 4 times 4 matrix, right? This is a 4 times 4 matrix, apparently. Okay, that's nice. Now, what do we know actually? We know that H depends on Q, right? So we know that H is a function of our joint coordinates, okay? So having said that, what is then H dot? Well, this is just a, the chain rule. Essentially, H dot is the partial of H with respect to Qi times Qi dot, okay? And you sum over the Q's, okay? Okay, and yeah, I don't know if this makes a big difference, but we can write this by taking the H inverse into the sum. So we have the partial. So we have the partial of Qi, Qi dot. Now the thing is that this is something we already identified somehow. Okay, let's say yeah. How did we, in the end, when we had an open kinematic chain, right? How did we express the twist in terms of the Q dot? Yeah, the Jacobian was there, right? Exactly. So it's also true that V is J times Q dot. And of course, I mean, you can write this like, exactly, no, this was a mistake. You can also write this as exactly like the sum of Ji Q dot, okay, I dot. And of course, I goes from 1 to n. If this is true, and I mean, you can, so this is the 6 vector thing. And if I plug if I plug this into this 4 times 4 matrix, so I make a hat on top of it, then of course, well, we can do this, for example, like this. Okay. So then essentially what you're getting is what? If this is the same, I mean, apparently they must be the same, right? So that means that the partials, I mean, this ith partial is essentially the ith column of the J, right? So saying that this is nothing but the Ji hat, and this is again, this was the instantaneous screw coordinate of our of joint I. Now I didn't actually write any indices in here. Why? Because we are implicitly saying the C, which is so again C and H is the same with my my presentation, because the C with respect to the H is always the one of the last body, because we look at the end effector of the robot, right? And that's fine, because then we know exactly how to express them, because you know that the Ji, if you remember, we had that explicit form by saying this is nothing but the joint screw coordinate, joint I, represented in the zero reference configuration, transformed to the last body, right? And this goes by HNI, which is the, so what is HNI? HNI was again the, what is it then? It should transform to N, that means like this, and it goes from I. Okay, so I to N. And there we go. So what the conclusion is exactly what we had here. Now, if you, and this is always the same idea with the Jacobians. I mean, Because now this Jacobian, of course, has to do with velocities, right? But you can also say, instead of having velocities like d, so what do we do? Goodness, what do we have here? So this is, of course, dq dt. You can also say, for small displacements, and you multiply the whole thing by dt, then what you get is, like, if you multiply this with dt, what you get is an increment of the pose. And if you forget about all this dt and say this is a finite kind of differential, then the approximation is like this. But anyway, I mean, this is what you have here already. So this identifies J. And then we are almost at what we want to do. So what I can do, I can bring this to the left, right? I can say, okay, this is delta C minus I is equal to the, yeah. And the thing is, when we didn't introduce it yet because we never used it. But if I have, for example, a 4x4 matrix, as I was saying, I can extract the 6 vector, but I need some notation for this, right? And because this is the hat, and it looks like as it looks like, and the inverse is just you swap it. I mean, you flip this thing. So when you have a 4x4 matrix, the V, so to say, the V operator is just the opposite, right? So it takes a because this one is a 4x4 matrix. The delta C minus I is also a 4x4 matrix by definition, because everything is a 4x4 matrix. So then we have here a 4x4 matrix, and I extract by this V operation the corresponding 6 vector. And that's almost the end, because now I have, yeah, that's what I'm saying. Exactly. So yeah, you see, this is just the opposite operation. And that's it, because now essentially what we have is like, so we can invert this, we can invert this Jacobian, okay? Assume that we have a non-redundant system for the time being, and assume that we are non-singular, which is most of the time the case. So we can say J inverse times delta, no, what is it? J inverse multiplied from the left to this expression gives you delta Q, okay? And so we have a solution for the delta Q. Of course, this is kind of a finite approximation. That's what we said, right? So you have to repeat this, and as you said, this is a kind of a Newton or Newton-Raphson iteration scheme. So you start from a certain configuration, like Q, then you compute this, then you define delta Q, then you define your new function, your new Q as Q plus delta Q, and then you repeat everything again, and it converges quadratically most of the time. Yeah, and that's it. So this is what you should use for solving the inverse kinematics. Of course, there are, so again, the inverse, of course, does not always exist, in a sense that it might be a non-square matrix, okay? And if this is a non-square matrix, of course, you cannot just invert it. You have to take a pseudo-inverse. For example, this Franca-Emica Panda robot, anyway, it's a 7-degree film robot. We have one Revolute joint, then the second, the third, the fourth, fifth, sixth, and there's one more 7. So you have a 7-degree of freedom system. And then what do? You take the pseudo-inverse, all right? You said it already. And exactly, so and we call them kinematically redundant. We talked about this yesterday. We talked about this yesterday, what it means to be kinematically redundant. You have more joint degrees of freedom than you have end effector degrees of freedom. Essentially saying this is 7, and the end effector can have maximum 6. I mean, our space is only 6 dimensions. Yeah, and then you take the pseudo-inverse. Maybe we should not go into the details of the pseudo-inverse, because yeah, that's not our topic. Okay, so this is essentially what I wanted to finish with the inverse kinematic solution. Yeah, any questions? I mean, oops, that was a bit. Essentially what you have to do is that step here. So you have to compute this part. So you compute delta C, by simply saying delta C is the current inverse minus the desired, and then you subtract the identity matrix, and that gives you a skew-symmetric matrix. A 4 times 4 matrix. It's good, a twist matrix, and then you multiply with the inverse of delta J, and then you get delta Q, and then you have your first guess for the inverse kinematic solution, and then you repeat it. Okay, I understand that there are no questions. If this is so, then let's finally come to the topic that is included in the title. Yeah, so finally, today's 20, no, what, today's 28, right? Yeah, somehow I mix up the dates. Anyway, so this will be 28, I guess. Yeah, motion equations of PKM. So this is what we actually did on Monday. So on Monday, we looked into principal differences of PKM of parakinematic machines and the standard open kinematics chain robot. They call it serial robots. Okay. So yeah, and we had we looked at two examples. One is this like 3D translational robot, and then the good old Gauss-Stewart platform, also called Hexapod. So this has 6 degrees of freedom, the platform, and this has 3 degrees of freedom, only translations. Okay, and then we looked into the topology, so the kinematic topology, as we call it, and we asked ourselves how to actually represent this. So how do you represent the topology of a robot in general? By using a linear graph, right? So the vertices are the bodies, and the edges are the joints connecting the bodies. And we kind of realized that for PKM, we have an interesting, nice structure because we have the ground, so that gets the index 0. We have the moving platform, in this case it's 10 maybe, and then we have like similar, or let's say identical, kinematic chain, and they call it legs, right? Like leg or limb or something like this. Okay, so and in this case we had the platform connected by 1, 2, 3, 4 joints. The first one here, number 1, 7, and 4. These are the actuated joints, so the prismatic joints that somehow motorized. Anyway, and the topology looked like this. And now the question is, can we capitalize on this topology, on this similarity? Because what you see is that it looks repeated, right? I mean, if you cut off the platform, for example, it would be all the same, right? And now the question is, can we do something? So if you go and look into the standard approaches in multi-body dynamics, right, or even in mechanisms, or even in robotics, people still do this. Well, you identify the loops, right? So we have 1, 2 loops here, like, for example, like this and this. As you said at the beginning, they are not unique. I mean, you can have like this loop instead of the yellow one, and then still you have 2 loops. So the number of loops is unique, but the loops themselves might not be unique. Anyway, so then what you could do is to say, okay, I define so-called cut joints by saying that I can. So what we said at Monday was it? We can, for any graph, we can introduce a spanning tree. Okay, a spanning tree, and you get it by cutting, for example, these 2 edges, which would be the edges, for example, corresponding to this joint and that joint. That's why we call them cut joints, because virtually you kind of remove the joints, and then you have an open kinematic. You have a tree structure system. You have no loops, so to say. Okay, because if you assume that they are not here anymore, then you really have an open kinematic structure, and that looks like this, right? So because essentially, if you cut them open, then this is the system you're looking at, and then what you could do, and what is done in general multi-body dynamics, is to formulate the kinematics and the dynamics of this system. Okay, so in this case, we would have one kinematic chain to the ground, fixed to the ground with 1, 2, 3. Is it true? No. One. What is it? 1, 2, 3. Yeah, 1, 2, 3 joints. Yeah, this is the same here. And the other one, again, 1, 2, 3 joints, and the other one would have one more body, right? 1, 2, 3, 4 joints. Okay. Anyway, you then would formulate the kinematics and the dynamics of this system, which is corresponding to this tree. And then what you have to do, because this is not what you, I mean, this is not the system you wanted to model, because the system you want to model is the one with the closed loops, right? And then you have to impose, again, like we talked about this constraint ranges. So you have to impose constraints, geometric constraints corresponding to the joints, and to the cut joints. And in this case, again, it's all regular joints. I mean, except the 3 at the beginning. And then you would have to impose the 5 constraints for each of the joints, for each of the regular joints. You can do the same, of course, for the hexapod and so on. You see that here the kinematic structure looks similar. You have 6 times repeatedly the same kinematic chain. I mean, these limbs here, the legs are all the same, kinematically the same. Of course, they might be different in the physical, embodiment, but kinematically they're all the same. What you could do, you could, instead of doing what I've been saying, you could say, okay, why don't I just split? I mean, why don't I just split the kinematic graph into the subgraphs corresponding to each of the leg, to each of these connections from the ground to the platform. And this would be like, so I have this one, this one, this one. So I would have like, and I can index the joint, the leg. I mean the leg, limb, strut, whatever you would call it, with L from 1 to 6, because you have 6 of them, right? So each of them has joints. Has 1, 2, because the universal joint has 2 regular joints, essentially 1, 2, and then we have 3 here. Okay, so 1, 2, and then we have 3 here. Okay, that's what you could do, what you can do. And this, by the way, so this looks very simple in the sense that we have, after splitting, we only have open kinematic chain, right? And we know exactly how to model them. We know exactly how to model open kinematic chain. We know the kinematics, and also we now know the dynamics, theoretically. And that's fine. And the same, of course, is true for this one. We know how to model this. But there are other systems like this. The most prominent example is the Delta robot, the one that is used for this high-speed pick-and-place operations and so on. But what you see in the topological graph is that you have these closed loops in here. So you have the, I'm not sure where it starts actually. So this is maybe the fixed platform, because it's hanging down normally, right? So you have the fixed platform, and this is the moving platform. And it does like picking stuff, right? And yes, and within this kind of mechanism that goes from the base to the moving platform, we have these closed loops. There's one here, there's one here, there's one here. There are other examples like this one. So this is a 3-degree of freedom mechanism. It can only do translations. Okay, I mean most of the industrial data, they have one more axis, which is an extra spindle that is actuated separately. So you have 4 degrees of freedom, but essentially this mechanism, the original delta mechanism, is just a planar. Just a spatial rotation, spatial translation. Then there are, as we call it, lower degree of freedom of these mechanisms. For example, this one. So there's the platform, and this platform can only move in a plane. So when I say in a plane, this is like this plane. So the platform can only move in this plane. And again, what you see here, we have closed loops. Here you even have more closed loops than here, because we have one here, and then you have one here. And then you have, again, maybe not easy to see, this is the same copy, right? So you have one here and you have one here. So, and this essentially gives you this mechanism. And if you look at the mechanism itself, it's like this. So this is what it does. And it can only move in the plane, in this plane here. Okay, so then modeling this is different from what we said, because if you look at the kinematic topological graph, for example, of the Delta robot, then you see immediately that you have these loops within each of the limbs, right? And now, of course, what you can do, you can of course split the limbs. I mean, you can separate them, 3 of them, and model them separately. But still, what you have to take into account are these loops, right? And that makes it a bit more difficult. It's all doable, but we should not go into this. The same is, of course, for this mechanism. If you look at the topological graph of this, they call it IRS spot. There's now the second version. It's for France. And what you have here is, of course, this topological graph. You see immediately that we have now we have four kinematic loops in the whole topological graph. But if you split it into the respective limb, that one and that one, each of them has one loop, right? So it makes it even more complicated. Yes, and maybe the terminology, and this is why we call them complex kinematic limbs or complex kinematic connections. I mean, because it's not a single, in contrast to this one, for example, it's not a simple kinematic chain. In mechanism theory, they call simple kinematic chain if you just have link, joint, like a zero chain, right? And that's nice. So this is what we had for the hexapod and also for this one. They are called simple limbs, okay? Whereas, of course, here we have complex kinematic chains that connect the, as you see it here, that connect the, not sure which one is what, the base to the platform. And they're not simple, they are complex kinematic chains because you have loops within the limbs. Okay, good. And we should we should focus on modeling those systems with simple kinematic chains. That's enough for the time being. So the modeling, of course, goes like this. You construct a kinematic topological graph, and then you identify, fundamental loops if you like. We don't have necessarily to do this, but what is interesting is you might cut off the platform, right? So if you cut off the platform, you end up with these. If you forget about these dashed lines, then you end up with these identical branches, so to say, which each of them, just to make it clear what we were talking about, each of them corresponds to one of these limbs, right? Okay. But you can also say that I'm considering what happens if I just copy, for example, this limb here, including the platform. And this is what we're going to do. So we are actually copying just this limb, including the platform, 3 times. Okay? And because they are similar, we can derive the kinematics and the dynamics, and then use it to find the kinematics and dynamics of the complete system. Okay, so this is what we're doing. Just maybe a bit more detail here. So now we have this for our PKMs with simple kinematic, with simple limbs. That means that we have just simple chains going from the platform to the ground. We have a certain number of fundamental cycles, and we can always find or define the cycles so to go like this, so that we always go and include the platform vertex. Okay, and when you have such a topological graph with, for example, gamma fundamental cycles, and remember this gamma was this Euler number or this cyclomatic number, which is just the number of fundamental cycles, which is unique for the graph once you have given the number of nodes and edges. So, and what you see immediately is that we always have one more limb than fundamental cycles, right? If you copy this one, then you will see you have exactly always one more limb than fundamental cycles. Okay, good. And now comes a bit of detail, which we should maybe only go briefly for the interest of time into. So let's say we have separated this one, and let's take this 3 degree of freedom PKM as an example, okay? And look at this limb here, okay? So we have now the platform connected to the ground by 1, 2, 3, 4 joints, okay? The platform velocity that you can generate with this open kinematic chain, right? Just imagine this is separated. So what do you get? You get you translate, of course, with this joint in the x direction. Then you do a planar motion apparently, because this revolute joint 3R mechanism does some motion in that plane, in the in the YZ plane. Okay, like in this plane. So you certainly get translations in X, Y, and Z independently. That's why we have the X, Y, and Z linear velocity in the twist of the platform. Okay, and then should be obvious because that does due to the revolute joints, you get this planar motion, which also includes rotation about the the one axis, and that's why we get this omega x. Okay, so now we have apparently again like a forward kinematics of an open kinematic chain, but this open kinematic chain in this case represents the limb, including the platform. Yes, and what you can of course do, and this is what we did already, you can define a Jacobian. The Jacobian multiplied with the joint velocities gives you the velocity of the platform when it is only connected to the when the platform is only connected to one limb. Okay, and to confuse you, we need to have more notations. So VPL is the twist of the platform when it is connected only to the platform, only to the limb L. Remember that we numbered them. So we numbered did we? Yeah. We numbered the individual limbs by L equal L from 1 to as many as we have. In this case, we have 3. Right? We have 3 limbs, 1, 2, and 3, which is this and this and this, and then this is it. So, so VPL is the twist of the platform when only connected to limb L. Okay, fine. The joint angles, because we also need a vector for the joint angles, right? We call them theta, and we call them theta L, L for the limb. And I use brackets because somehow we have to distinguish if this is an index of a joint or something. No, this is the index of the limb. Right. Then we know that, I mean, this Jacobian has a certain rank. So, I mean, if it, in any regular configuration, it has a certain rank. So, and we call the rank RL. And what we assume, and this is most of the time the case, is that this limb, I mean, yeah, this single limb is non-redundant. When I say non-redundant, as we said yesterday, what does it mean? If I fix a platform, this cannot move, right? Which means there is a unique correspondence of the joint. Unique. Anyway, you know what I mean. It might even not be unique even in this case. Anyway, so this is it, right? So it's a non-redundant. And then what we also assume is that the degree of freedom of the platform, of the PKM, is not greater than or is equal or less than the degree of freedom of this kinematic chain. Okay, what I'm talking about is the following. Now we concluded that the platform, now I can ask, what is the degree of freedom of the platform if it's only connected to this limb? No, I mean the platform can, the platform can rotate it. So we have this kinematic chain, right? That does this planar motion. It does also this translation here. And then we concluded this is the platform twist, the possible platform twist. Yeah, exactly. It's 4 because you have 4 components here. So you have the x, y, z translation and the rotation about this axis. All right. Okay, good. Okay, yeah, that's fine. So, but how many degrees of freedom does the platform have when the whole thing is assembled? Like here, how many degrees of freedom does the platform have if it is assembled? It was 3. Simply because, why? I don't know why. The rotation has been restricted, correct. So let's say we look at, again, maybe this limb. This is what we had in the other picture. So this could do the planar motion plus the orientation. I mean, the rotation about this axis. Now, the rotation about this axis is prohibited by this chain, right? Because this cannot, this kinematic chain can only perform rotations about that axis. So it means that actually it restricts the motion of the platform to, so to say, to the intersection of the two motion spaces. So they can perform translations in space and rotations about this one. This can perform translations in space and rotation about this axis. So the only thing that is common to them is the translation in space. And the same is for this one. So eventually we have 3 degrees of freedom. But that's important because, we have to take this into account, because eventually our robot, our PKM, will have a degree of freedom that we call, delta P. Delta P is the degree of freedom of the platform, which is maybe less than the degree of freedom of this kinematic chain. Okay, what else can we say? We have to talk about task space velocities. So when we concluded that we have a certain number of independent outputs, so to say, of velocities that the platform can perform, then we can restrict our vector, our twist vector, to exactly these velocities, and we call them the task velocities or task space velocity of the separated arm or separated limb. Okay, this one just alone can have this kind of velocities. Okay, and we get this from the twist by just eliminating the zeros. Okay, and correspondingly, when I eliminate these zeros, then of course in the equation that we had before, like this one here, I have to eliminate the the second, third column. Okay, and the corresponding Jacobian that we get when we delete them, we call it JT. So you see lots of terminology, but not really something new. Okay, so now we have a Jacobian that has what is the size of the Jacobian? It's a 4 times 4 Jacobian, right? Because you have the 4 outputs and we have the 4 inputs. We have the 4 joint angles and we have the 4 velocities. Okay, wonderful. And that's what we call the task space Jacobian. As I was saying, like pictorially, it looks like this. You take, what's this now? Yeah. JPL, where's JPL? We don't. Now I'm getting confused a bit with my own task comprises report of GPA. Yeah. Yeah, anyway, this is what I said already. Okay, so we have the task space velocity of the assembled velocity also to be considered. Because remember, I said bracket L is the task space velocity of the platform and only connected to this single limb. If the whole thing is assembled, right? If the platform is connected to all the limbs, it means that the PKM is completely assembled. Then we have a certain velocity again, and we concluded already it's only the ones that comprise the linear velocities, the spatial linear velocity. Okay, and we give them the name VT, and you see you just omit the L because now it's the one that is specific for this particular PKM. So, and in our case, our PKM, this one here, can only perform translations. Okay, and of course it has the same size as we have degrees of freedom of the platform. Right. Generally, the degree of freedom of the platform is less than the maximum rank of our Jacobian here. Okay. Yeah. So what was the Jacobian rank? It was 4 because you can have 4 independent outputs here, right? You can have 4 independent velocity generated if you don't assemble it. If we assemble it, it reduces it. But still, the rank, of course, is of our 4 times 4 matrix is 4, which is nice because we can invert it. But generally, it is less than the platform degree of freedom. Okay. And in order to make sense out of this, it's a bit of a crash course today, I know, but we have to finish this. In order to make sense out of this, we should actually introduce some metrics that somehow relate the task velocity of the PKM, which means the 3 translations, to the task space velocity of the limb when it is only when it is separated. Okay. Now we concluded that the platform of the separated limb can have the 4 velocity components. We also concluded that the first one is not possible when the PKM is assembled, which means that we have to have some sort of a restriction. Now, what we're saying here is the task space velocity of the limb is then given from the admissible task space velocity of the limb is then obtained from the task space velocity of the PKM by just using that matrix. What does it do? You have a 0 column, 3 zeros, and then we have the 3 identity matrix. So essentially what it does, it takes your task velocity, okay, puts it into the last 3 components in this VT, and then it multiplies whatever comes out of here with 0. So which means that you have 0, Vx, Vy, and Vz. Okay, and this is the admissible task space velocity in the end. So we kind of implicitly impose the constraint that the platform cannot rotate, and we relate the task space velocity of the platform to the task space velocity of the disconnected limb. Yeah, and then we're almost there, because now what we can do, we can use the Jacobian of the limb, the task space Jacobian of the limb L, to express the task space velocity. Now we set the task space. So what I'm saying is that this is what we had before. We said the task space velocity of limb L is just given by the task space velocity Jacobian times Q times the joint angle time derivative. So just this one as a kinematic chain. And now we said, okay, but this is related to the task velocity of the PKM by this relation here. And what I can say now is that I know that this J was invertible, right? Remember, it was for this case a 4x4 invertible matrix, okay? Which means that I can invert it, okay? And this is the key step actually, because now what I can do is I can express all the joint velocities in all the limbs, okay, by using the task space velocity of the PKM, like the x, y, z velocities, okay? So this is the idea. And I can do this for all the limbs, which means I can actually express this if theta, I mean, the big theta is just the theta of all the limbs. So I have the coordinates of the first one, second one, and so on, and of course I line them up. And I can compute them from the task space velocity with the matrix F. And F is just defined by, lining up all these equations for the limbs, and the limbs go from 1 to capital L. Okay, and that's it. So this is the main step behind this approach. And what is important to realize is that this D implicitly formulates the constraints by using the 0, the constraints on the platform motion. Okay, good. There we go. What's this? I don't know what this is. Yeah, okay. I don't know what this is. Yeah, this was just a hint. So, and that's basically it. But maybe to understand it correctly. So what I'm saying is that what is this equation doing? I mean, this is good to understand it. Maybe the steps you have to follow up. But what is this equation doing? It's like that you move the platform of the connected, of the assembled PKM. Okay, so assume that all the limbs are connected. Then you move the platform, and then according to this platform motion, you get the motion of all the joints, the velocity of all the joints. And this is the key element here. What you can say, this is kind of a generalized inverse kinematic solution. Okay, because out of the platform motion, you get the motion of the limbs, of all joints actually. And that essentially is it, because the only thing that you now have to do is to look into dynamics. And for the dynamics, you do the following, because for the dynamics, it doesn't make sense to copy this limb, for example, including the platform 3 times. Because then we would have two redundant copies of the platform, right? So that's why we go back to this idea of saying, okay, we eliminate the cut joints in our topological graph. So let's say we have the two loops here. We eliminate this one and that one, for example, and then we're ending up with this kinematic tree structure. And then, of course, we have the joint coordinates. They are different now. Again, new notation. They are different in a sense that, of course, for example, for that limb, you're missing this joint, right? So that's why we have either we have for this limb we have 4 joints, here we have 3, and we have 3. Okay, but this is the only difference. Okay, and that's essentially it. Because now what you can do, you can of course express again the coordinate, I mean the velocities of all the joints in terms of the platform twist, and that's it. So and that's exactly. So and that's what goes into the motion equation. Again, this is the system we look at. Okay, that's the system we look at, and we know how to derive the motion equations somehow. I mean, yesterday and the day before we started doing this, the dynamic motion equations of each of the limbs looks like this: mass matrix, generalized acceleration, Coriolis term, and the gravity if you want to, and maybe some actuation forces here. Now I would like to assemble it. And again, there was we talked about constraint wrenches, constraint forces and torques, and we have to include them here, right? Because what I want, of course, is to model the assembled system, not this kind of funny cut open system. Okay, and that goes always the same. If I assemble it, there must be some constraint forces, right? If this is so, then I can again invoke this principle of virtual power, the Jordan principle. And how does it go? I'm saying that, and this is the key again, I say that possible velocities, of course, I mean admissible velocities of the assembled system, that's the important thing of the assembled system, as we said before, given in terms of the task space velocity times this matrix. And the only thing I have to do, I have to take the variation, multiply this from the left here, transpose, and there we go. Okay, and this is what you get in the end, because you multiply this equation from the left transposed, from the left with the f transposed. And of course, what happens is this is always the same. Reasoning, saying that the constraint forces, they do not perform any work on admissible velocities, which means that this goes out, and the final equation is like this. So you have to sum up the these equations. I mean, for all the limbs, multiplied with the this F matrix that transforms task velocities to the joint velocities. And in the end, if you so again we have the Q dot in here, the theta dot and double dot. You replace them using this equation. So you plug in, for example, this term for here and the time derivative of this in here. And if you do the math, then what you see is that again we get because then of course the only thing that remains is is v, the task space velocity of the platform, that goes then into this equation, and the whole equation is given. The dynamic motion equations are given in terms of the platform twist, this vt of the assembled system. And of course we have this form here again, which is again a generalized mass matrix. Okay, it is of course symmetric, and it is also positive definite. And then you have these terms here; they look all the same structurally as we had it before. Yeah, so these are the motion equations for a PKM, for a parakinematic machine, in task space formulation, right? Because these are the motion equations using the platform twist, platform velocity. And I shouldn't say twist, right? Because this is just those components that are really possible for the platform. In this case, pure translations, right? A twist is like a 6-vector. A twist is a proper, omega and v. But anyway, this is, yeah. Okay, that is essentially it. What else can I say? I can ask for questions. You're going to get the slides anyway, so it's all in there.
Yesterday's slides got forwarded.
I know I did not forward it to you, but you're getting this one and also from yesterday. Yeah. You got one of the paper. No, there's actually this document. There was a document. There was a PDF called Parallel Manipulators or something like this, right? Yes, and you got it already. And that is actually a chapter of a new book. You know, this robotics, the Handbook of Robotics. Handbook of Robotics, the big book. You know, the Siciliano book, Handbook of Robotics. And there's a new, like a follow-up book. It's called Roboticos MOOC, MOOC, which is massive open online courses and so on. And there's a book on this. And I was contributing this chapter. So this chapter is essentially covering all this stuff with the PKM. But in any case, if you have questions, want to discuss more details, you can anytime write to me. For the PKM, you mean? Same story. Same story. It's not unique. Oops, sorry. Same story. It's always the same. When you, I don't know, maybe stick here, whatever. Yeah, we can look at this one. It's the same story as we did at the beginning of today. You have to solve the geometric inverse kinematic problem, right? And that is normally not that easy. The good thing is for PKM, the inverse kinematic problem is easier. For example, for this one, the inverse kinematic problem is pretty straightforward because what you're given is the platform pose, and you're asking for, I don't know what you're asking for. I mean, usually you ask for the model, you would ask for all the joint angles, right? For the control, you would only ask for the length of these struts. And that's pretty easy because once you have the platform, you know the attachment points, and then you can compute the length and so on. For here, what about this one? Is it easy? It's actually doable to have it in closed form solution, right? So once you have the platform, you kind of can compute with a bit of trigonometry the angles. But again, this is not unique, right? Because this goes this way, but it can also go this way, right? So for this system, it might be possible to have it in closed form, but in the general case, you would do again this iterative Newton-Raphson iteration scheme. Yeah. I mean, for PKM, the forward kinematic is a problem, right? Because, for example, I mean, this is this old topic people have been working for 20 years, more than 20 years on. It's like I give you the length of the actuators. So this is what you have in your encoder, right? So this is what you're controlling. You control the length. Now, if you have the length, how do you get the platform configuration? So for the same length, the platform, for example, can be swapped over, or it can be. It's not unique, and that's a bit of a headache. But there are ways of doing it. Yeah. Good. Someone was asking, why don't we use kinematic control or something instead of force control? But the thing is, what is kinematic control? Yes, that's right. But as a matter of fact, I mean, you can only control forces, no velocities. I mean, even if you have like you have maybe an industrial controller and you have a force control. There's a PID or PI controller that supposedly does velocity control. But in the end, what happens is you give a velocity command to your motor, but the motor generates, of course, a force and a torque. The only thing is the level of abstraction. I mean, how far do you go to the model? I mean, how far does your model go to the lower level, to the force and torques? And of course, for underwater vehicle, it makes sense to go, and for flying, for UAVs and so on, it makes sense to really look into the forces because I mean the forces is essentially what is driving your system, and there wouldn't be a good kinematic equivalent actually for this. I mean for the robot, when you have a joint angle and you have a unique, I mean you have a joint angle and this corresponds to maybe to a joint torque, it's kind of easy to relate them, right? But for a flying object, for example, when you have a propeller, I mean there's much more dynamics going on. So just looking at the speed doesn't really tell you anything about the force, the thrust force. So I guess this is the reason for doing it. I mean, eventually, these model-based control schemes, they all do force control, at least the feed-forward part of force control. And remember that we had this the motion equations. There were two uses for it, and one is actually the one that we use in control, which is the feed-forward control. So we evaluate, but essentially the last thing here, what you do here, you more for the PKM, you would actually prescribe the motion of your platform, and then what you get out here is the input forces that you need. But of course, only if everything is correct. If the model is perfect and there are no disturbances, your encoder are super good. Of course, it's not perfect, but it gives you a very nice kind of steering towards the trajectory that you want. And then, of course, you have to close the loop with the PID controller. But the PID controller, any linear controller, is linear. I mean, assuming a linear system, and we are having a non-linear system. This is also called feedback linearization, so that you kind of linearize your non-linear system by using a feedback loop. Or let's say feed forward. Yeah.
What are the different control methods that we can use when underwater vehicle or drone for this controlling? Because the system equation is fully non-linear.
Yes, correct.
Then which control approach is best, please?
For the underwater vehicle.
Underwater vehicle or any aerial vehicle also. Because this is that will.
Well, there's lots of research going on. Essentially, you have to construct your own controller. So you have to, I mean, the standard approach, you have to find the easiest way is to find the Lyapunov stable control system. So you find your Lyapunov function, and then you do your controller, and you show it stable at least. But then you have to tune it. I mean, for the underwater, I mean, for flying systems, this is still maybe not. I mean, there are different approaches, and there are different opinions which one is the best. So you have to see. You have to look at your system also.
We use PID control in there. There are still errors. There is one error in one part, but the error will keep on increasing.
Absolutely.
Because vehicle is this, and then we will have a manipulator and we will have a separate links on. And that error will be. At that time, we have to use for every link we have to use separate controller, or one control can be used for.
Well, this is the thing. Okay, so now the question was, do you have an air vehicle? So let's say an underwater vehicle. So you have a moving platform, and you have a robotic arm on top of it. So for the robotic arm, you could use, of course, what we used before, like the PID controller with the non-linear feed forward, maybe. And then on top of it, or before, it depends how you call it, you should control the platform. It's absolutely right. I mean, it's an absolutely legitimate question to say, why don't we actually control the whole system together? And that, in my opinion, is what you should do. Yeah. Yeah. To develop one holistic controller.
Which control scheme can be suitable for this full system control? Because there are different control systems.
I wouldn't make any statement on that. There are different ways of doing this, and it's ongoing work. Yeah. So to conclude, I would like to thank you very much for the engagement and the discussions that we had. It's nice to see that people are interested in. I know it's all new. It's all, you have to digest it, and maybe certainly not all of this was relevant to everyone, but maybe some parts of it is something that you take away, and at one point in life or in your research, you will find it useful. And anytime, if you have questions, you can always contact me or Yogesh.
So
thank you very much for this particular session. So now we have 10 minutes break. Okay. Then after we will start the next session, that is the last one. And followed by that one, we have again you inform others to come for the examination at least 3:15. Okay. So it is a multiple choice questions. Okay. So not more than 20 questions. So, so accordingly you act and then you inform your colleagues to come for the questions. Okay. Means the examinations. And then we
Starting time is 3:45.
3:15.
3:15.
3:15 is the study time.
If the time someone is about 2:30,
2:30 why?
because I have missed the presentation.
Where? But lunch is at what time?
That's idea nights or
I can be like 2 p.m. Okay, so if 2:30 then again for validatory we have to come. Na? Do you have paper? Presentation? I don't think which paper you have.
MTech one.
And since Sunil sir. Okay. At what time? 3 p.m. Na? Or you can try to come between 3:30 or okay, 3:30 we can say 3:30 to 4 is your exam. You can post it there. 3:30 to 4 is your exam, and 4 onwards we will have our validity. Because I have given mail, when what will be what time is the validity? 5. Supposed to be. Okay, let me see. Switch on this one.